Newton's law for uniform circular motion, you have sum of the forces centripetal equals minus mv squared over r. Right? That's uniform circular motion.
Right.
That's Newton's law for uniform circular motion.
But this was
What's that?
And you use Coulomb's law.
Yeah. Yeah. So when you look at this thing, you say, okay, what other? So look, I can draw. Here's F Coulomb. In what direction is my acceleration? My uniform circular motion acceleration, my centripetal acceleration.
R.
It's what?
R.
It's R. But sometimes I get messed up because I usually say outwards is positive, and I start with the electron. All right. So if I'm
negative R.
Yeah, well, the deal is here. If outwards is positive and I'm doing it around the electron, then I have to make this positive too. All right? Because usually when you say uniform circular motion, you're usually thinking about the origin. All right? But now I'm shifting my origin to the electron. All right? So I'm going to make it positive because it's outward from here. That's where my acceleration is definitely this way, and F centripetal. My centripetal acceleration always goes inward radially, and I'm going to just say that's positive in this case. And what is the direction of my Coulomb force?
In the same direction as
it's going to be the same direction. It's outward, so that's going to be positive. So when I come over here and I add up these things, I add up all the forces that are there. I have the Coulomb force. All right, so the Coulomb interaction. So what is the form of the Coulomb force?
Q squared over R.
Q squared over R squared.
Okay, so K
Q more than Q2
over R squared.
Yeah, it's the same charge.
Okay. So that's what I have. So this is my classical result so far. Okay, now there's the problem though. It's also known that accelerating charges radiate. All right, and how do people know that? So if you take any type of charge and you put it through you make a battery and then you charge, you make two plates and you charge them and you introduce a charge. The charge will accelerate. If it's a minus, it will go from the minus side to the positive charge, the positive side. And when it accelerates, you get X-rays. Or you get radiation of any given frequency. That depends upon the potential difference. All right, so if you radiate X-rays, or you radiate radiation, and radiation carries energy, can you get energy from nothing?
No.
Okay, so therefore, what has to happen to accelerated charges? To their energy. They lose energy.
It's spiraling.
Okay.
It would be stable.
That's right. So in this case, if you have an accelerated charge that radiates, what's going to happen is the total energy of this electron is going to get lost and lost and lost and lost until it spirals in and crashes into the nucleus. And as it does that, it's going to be giving off radiation. And that's what you would call, that's one form of the ultraviolet catastrophe. That you'd have no stable atoms. None of the atoms would be stable at all. Alright? So that's a big problem. Alright? That you do have stable atoms. Things aren't unstable like this. The other thing is about this time where you're also getting things like spectroscopic information. And the spectroscopic information had to do with the lines, the discrete lines of light and energy that you got out of the hydrogen atom. And they were like the Balmer line, the Pasha line, and a Lyman line. I think those are the three main ones. Again, this is modern stuff, modern physics, stuff we go over in detail in modern. And what happened is when people were looking at that, they were able to spectroscopically see the discrete energies, and they came up with a nice formula that were able to predict and get those energies right. Right? They didn't know where those formulas came from, and they had a whole bunch of constants. They had all that stuff that they could predict these lines, but they had no idea where it came from. All right, it just worked. All right, so those two people, but atoms are stable. They don't disintegrate. They don't radiate away.
Was a positive result of the Bohr model that it showed the radiation was proportional to drop in energy levels?
Yep, that's right. So that's another big thing that came out of it. But and it was well-known spectroscopic formula.
But they also noticed that that drop in energy level didn't correspond to the energy of the photon that was emitted. So that was a huge problem as well.
Well, let's get there, okay? So we had these two things. So what would you guys do? Classical physics is not working. All right, and then you come back here and you look at this big picture, and you start thinking about symmetry.
He took Planck's constant and like applied it to the atom.
Okay, that's right. That's right. So let me kind of give it some words here. Noting the symmetry, that you might like to have, and that light is wave and particle light. Well, perhaps the electron itself is also wave light. All right? And if it's wave light, well, then it has to share some of these properties that I'm talking about with light. And the newest kicker that got everybody out of the problems of the old physics was Planck's constant. Right? And what are the units of Planck's constant?
Angular momentum.
Okay, it's angular momentum. All right, and what we found out is angular momentum is quantized. So what might you say if you're Bohr?
That those angular momentum of those orbits are quantized at those discrete levels.
Of the orbit are quantized. So Bohr an angular momentum of electron orbits are quantized. And these orbits do not radiate. Transitions. So what Bohr says is you get radiation. That's a nice thing to put in here. You get radiation when electrons transition between stable orbits, between quantized orbits. This is kind of like a semi-classical approach. We're using a lot of classical ideas and throwing in some quantum ideas. Okay, so let's see where we can get with that. Okay. All right, so let's approach this problem. Semi-classically, we have K E squared over R equals MV squared over R.
R squared?
Where?
KE squared over...
Yes, thank you. Yep, gotcha. All right. All right, what do we also know classically? We also know that the energy total equals the kinetic plus the potential. So this is classical. All right, what is the kinetic energy equal? And again, I'm just talking about the electron. I'm not talking about the whole atom here.
Well, the mv squared, 1/2 mv squared.
It's 1/2 mv squared. And what is the potential energy?
That's the Coulomb force.
That's gravitational. Okay. But remember, if you take the electron and the proton and compute the gravitational force to the electromagnetic, it's something like 10 to the 34 times smaller. So gravitation does come in, but it comes in somewhere around the 34th decimal place. Right? And so for all intents and purposes, when you do particle physics, you don't do gravity. Right?
You're only worried about the electromagnetic force, which is the Coulomb force, and that would be the Coulomb potential.
So the Coulomb potential, very good.
Isn't it just KE squared? Okay,
Times the distance between them.
So it's KE squared.
over R squared.
Yeah, that's a force, right?
Oh, so we're just finding the
Potential.
So KE.
So it's KE squared over R.
Okay, that's right. So it's K. I'm going to write a little more suggestively. K Q1 Q2 over R. In this case, Q1 and Q2. And the reason that I want to do that is, what is the charge of the electron? We'll just say that's minus E. And what's the charge of the proton?
Plus E.
Plus E. So this is really 1/2 mv squared minus k e squared over r. I just wanted to make a suggestion so we can talk about that. Okay. All right, so here's nu. All right, nu is L, which equals angular momentum R cross P. All right, if we look at units, if the units of this are going to be, well, we already know the units of this. But if R and P are perpendicular, all right, so this is going to be the magnitude of R times the magnitude of P times the sine of the angle between them. We line them up. It's R and P. All right, and the sine of the angle between R and P, if it's a uniform circular motion,
Just one. Right? Or
angular momentum is always this way, so that you're going to turn it down. And V, and then here's R, zero poorly. But they're always perpendicular.
Right.
All right, so this just equals RP. All right, and what Bohr said is this is quantized, so that this equals n times h bar. Okay, here it's h bar. So in other words, R times mv has to equal nh bar. Okay, so this is new.
Where the h bar is different than h because it's the 2 pi is included because it's going in a circle.
Yeah, so when you do orbital angular momentum, you got to integrate over circle. Here's where that 2 pi comes from. When you do orbital angular momentum and you integrate over circle, a line integral over circle will always give you 2 pi. All right, and so you're always dividing by 2 pi all over the place, so you needed to use h bar over there. Okay. All right. So, homework for Thursday. Okay, from these equations, 1, 2, and 3. You can show that Rn, so that R, okay, let me make this distinction for n equals 1, 2, 3, and so on. Alright, so clearly I'm going to have a function of R, so I'll write it like this. Rn equals 4 pi epsilon naught h bar squared all divided by e squared m times n squared. Alright, for n equals 1, 2, 3 to infinity. And when you throw in the numbers, what I want you to do, and please do throw in the numbers, that this comes out to be about